Hello, this is a video for Mr. Haywood's statistics classes. I'm making this video in the fall of 2022, but I will most likely use it again. But if I make any strange references to, events that are no longer current, well, that's why. Um, but I wanted to go through some background information for your data analysis project. It's one of the projects that I want you to complete this semester. And there are some things that I need you to know how to do in StatCrunch, specifically for manipulating raw data, that you may not know how to do because I don't think we've really covered it so far in the class. So you can you should open up this document so that you can follow along and kind of take some notes, maybe print it off, so that you can take notes on it. Or at the very least, open it up and take notes on a separate sheet of paper or whatever. But yeah, open up the document, make sure you're following along. I'll let you read through the information here. What I mainly wanted to do in this video is just show you how to run some hypothesis tests from raw data. And I'm going to give you those examples using a different data set. So I'm not going to use the data set that comes from the class survey that I had you take. So the class survey was that weird one about cake flavors and superheroes and your height and all of that stuff. That's the raw data that I'm going to have you analyze. But I just wanted to show you, using a different data set, how you would do some of the procedures that we're talking about. So one of the things that I want to point out to you that may not be super clear at this moment is that we can think of a lot of the hypothesis tests that we learned about as a way to compare two variables. Okay? So a lot of what I ask you to do in the project is to compare how two variables interact. In fact, that's basically what the project is all about, is to compare how two variables interact. So you can determine what kind of hypothesis test to run by asking whether those two variables are qualitative or quantitative. And there are, broadly speaking, three possibilities here, right? It could be that both of the variables that you're trying to compare are qualitative. It could be that one of the variables you're trying to compare to another variable, it could be that you have one qualitative and one quantitative variable that you're trying to compare. And then it could be the case that both variables are quantitative. So if both variables are qualitative, then you would run a homogeneity of proportions test, which is, you also know, is the same thing as a chi-square test for independence. Okay? So if both are qualitative, then you run a chi-square test for independence. If one variable is qualitative and the other is quantitative, then you run an ANOVA test. And you run an ANOVA test in which you group your quantitative variable by the responses of the qualitative variable. So I'll show you an example of this in a second. And then finally, if both variables are quantitative, then that's where you would run a linear correlation. And in the past, we've talked about doing linear correlation analysis, regression analysis, but we didn't ever introduce a hypothesis test for that. Well, it turns out that StatCrunch will run a hypothesis test for it, and so I want to talk about that a little bit. So let's talk about each of these things in turn. Okay, I'm going to go ahead and open up this data set. You should do the same thing. So just go ahead and click on the link, and then it'll open up in StatCrunch. And in order for you to be able to manipulate any of this data, you'll have to then sign in. So go ahead and sign in as well. So you just sign in with your Pearson username and password. Oh, come on. And then you'll have access to the data set, and you can actually manipulate it and run different tests and make graphs and stuff. But okay, so let's say that you've got two qualitative variables that you want to compare. Maybe you think there's some kind of interaction, or maybe you don't suspect that there's any kind of interaction and you just are curious to know if there happens to be some kind of correlation between those two variables. Right? So if you have two qualitative variables, then as I said earlier, you should run a homogeneity of proportions test, or in other words, a chi-square test for independence. So looking at this data set, if I can find it. So looking at this data set, so first of all, this is raw data. There has not been any summarizing that has taken place here, right? And this is a data set that contains a list of all of the US presidents so far, and it gives us information about when their term was, how many days they served, what their state of birth was, their height, etc. So each of these columns represents a different variable. Okay? Each column in this spreadsheet represents a variable. So if I were in a situation in which I wanted to compare two qualitative variables, okay, but for example, if I wanted to compare eye color and political party, right, to see if eye color has any bearing on political party, right? Maybe for some strange reason, you know, blue-eyed people are more likely to be Democratic or something, right? Then we would run a chi-square test for independence, or a homogeneity of proportions test. We have not done that with raw data in the past. Usually the way we would do that test is we would arrange the information into a contingency table. But you can actually run the test with raw data. So you go to stat, tables, contingency, just like we would usually, but then you're going to go to with data instead of with summary. Okay? StatCrunch will then prompt you to select a row variable and a column variable. What you should select for the row variable is whatever you think the explanatory variable is. So in this case, eye color, because we're wondering if eye color predicts political party, right? So so you choose whatever your explanatory variable is for the row variable, and then your column variable is the response variable, in this case, political party. And then you'll run the chi-square test for independence and hit compute. So here's how that would look. So we go stat, tables, contingency, with data. For the row variable, we wanted to compare eye color and political party. Okay, and then you run the chi-square test for independence. So notice that it will spit out this nice contingency table for us. Okay. Again, we only had raw data, but it gives us a contingency table, which is really nice. Your p-value here is fairly large, so we are not going to be rejecting the null hypothesis here. The null hypothesis would have been that eye color and political party are independent variables, right? They have no bearing on each other. Well, we're not rejecting that hypothesis, right? Because our p-value is large. And that makes sense. I mean, why would eye color have anything to do with your political party? So, okay, so that much makes sense. Don't forget that you can always play around with some of these row percentages, column percentages, expected counts, percent of total, and so forth, to kind of investigate further things here. For example, if I wanted to know what percentage of, instead of just looking at the total counts of like what percentage of Democrats had, instead of looking at the total number of Democrats who had blue, brown, gray, hazel eyes or whatever, I could look at the percentage of Democrats who have those different colored eyes. And the way we would do that is we would want to divide, if we wanted the percentage of Democrats with blue eyes, we would want to divide 10 by 16. So in other words, we would want a column percent, right? So we could get all of those percentages that way. If I wanted to know what percentage of blue-eyed presidents were Republican, right, then I would want to do a row percentage, right? So I could change that to a row percentage, and then I know, okay, so amongst the presidents with blue eyes, 48% of them were Republicans, 34% of them were Democrats, right? Anyway, so you can kind of play around with some of this stuff and get some summary statistics this way. Another thing that I wanted to show you about this is about a graphical summary. Okay. So probably the best graphical summary for a comparison of a qualitative variable to a qualitative variable would be to make a side-by-side bar chart. And here's, as a reminder, here's how you would do that, right? So you go to graph and then bar plot, and then in our case we're working with raw data, so we'll say with data. And then under select columns, you'll choose the response variable, and under group by, you'll choose the explanatory variable. So we want to group by eye color in this case. Okay, and then the type of bar graph that you want to create is a relative frequency within category. Okay, so choose the relative frequency within category. So let me show you what that looks like. So we go to graph, bar plot, with data. The column that we want to select is we're comparing eye color and political party. So we want to make a bar chart of the political party grouped by eye color. Okay, and then we want to do a relative frequency within category bar graph. So we'll do that, and then we will hit compute. Okay, so it gives you this nice side-by-side bar chart where all of these blue bars correspond to blue-eyed presidents, all of the red bars correspond to brown-eyed presidents, and so forth. Okay, and then you have, you can compare Democrats, Republicans, and other. So this would be the relative frequency. Now I suppose you could do if you just did let's say like a frequency bar graph, it'll still give you a side-by-side frequency bar graph. This one is less, I think this one is a little bit less useful, because if you happen to have, in this case I think it's a pretty even split between Democrat and Republican presidents, but if you happen to have one group with a much larger share of, let's say that there were a lot more Republican presidents than Democrat presidents in the past, then all of the Republican bars would be taller than all of the Democrat bars, and that wouldn't necessarily give you good information. That's why I say it's better to make a relative frequency. If you just do a relative frequency though, instead of choosing relative frequency within category, if you just choose relative frequency, then what this will do is it'll take the number of blue-eyed Democrats, let's say, and divide by the grand total number of presidents. And again, this is a little bit problematic when you're trying to compare groups, because if one group has, a greater number of presidents or whatever, then all of those bars are going to be taller than all of the other bars. So that's really not what you want. That's why if you go with relative frequency within category, instead of dividing by the grand total, it divides by just the total of Democrats, right? Just the total of other, and just the total of Republican, and that's a more fair way to compare. Anyway, so that's what that would look like. Okay, so that's how we make comparisons between two qualitative variables. One last thing that I want to point out is that if each variable only has two different responses, then instead of running the chi-square test for independence, you actually want to run McNemar's test. Okay, and I can give you an example of this from the data that we have, right? So for example, if we wanted to determine whether handedness, right-handed or left-handed, has any bearing on whether the president died in office, yes or no. You notice how both of those just have two possible outcomes, right? Right-handed or left-handed, yes or no. So that contingency table is going to be a 2x2 contingency table, and for a 2x2 contingency table, we run McNemar's test. So here's what that looks like. So if we want to compare handedness to whether or not the president died in office, which by the way, I do not expect there to be a correlation here, but let's just see. So we would go to stat, tables, contingency with with data. For the row variable, we'll choose handedness. For the column variable, we will choose whether or not they died in office. So we want to know whether their handedness, is somehow correlated to whether or not they're going to die in office. Like, are left-handed people more likely to die in office, or whatever. But because it's a 2x2, we want to run McNemar's test. Okay, so we hit compute. And actually, we are rejecting the null hypothesis, which is surprising. So one of these groups is much more likely to die in office. I wonder. So if we let's look at some row percentages. So it looks like 12% of left-handed presidents died in office, whereas 19% of right-handed presidents died in office. So there is a difference there. In this case, I would say probably the reason you're getting this result, right? The reason you're finding that there's a correlation is just because the sample size of left-handed presidents is so small. I mean, you only have 8 of them, and so it's probably not even valid to run this test. In fact, let's look at the expected counts. Okay, yeah, okay, so the conditions to run the test are that all of the expected counts need to be more than 1, and it passes that condition. Then the other condition is that 80% of the expected counts need to be more than 5. And here we have this expected count, which is less than 5. The other 3 are more than 5, but unfortunately 3 out of 4 is only 75% and not 80%. So it's actually, so these results are not valid. We shouldn't even be running the test. Oh, you know what? I'm giving you the wrong information, though. This is McNemar's test. For McNemar's test, what we need to do is make sure that the off diagonal here adds up to be more than 10, which it does. I don't know. I guess this is statistically significant, but it must be some kind of spurious correlation, right? Anyway, that's how you make that comparison. Okay, so that's how you compare two qualitative variables. Now, if we want to compare a qualitative variable and a quantitative variable, the way we do this is we run an ANOVA. And once again, we have not run any ANOVA tests in this class so far from raw data. We've always had the data stratified by the qualitative variable that you're trying to discover if there's a correlation with. So if we have raw data, we can still run the ANOVA, right? You go stat ANOVA one way, but then instead of selecting the columns, you're going to click on values in a single column. And then under responses in, you'll select the response variable. And under factors in, you'll select the explanatory variable. Note that the response variable has to be the quantitative variable here. Okay, so as an example, if we want to know whether eye color has any bearing on height, eye color is qualitative, height is quantitative. Okay, so height is going to be our response variable. Eye color is going to be our explanatory variable. That's what we're going to group by. That's what we're going to say we put our factors in. So let's take a look. Eye color and height. Okay, let's take a look. So if I want to compare eye color and height, I would go stat ANOVA one way. Then I want to select values in a single column. The single column that I want to compute the mean of is the height column. So that's where my responses are. The column that I want to group by is the eye color, right? So those are my factors. So I'm going to put eye color as my factors. If you want, you can go ahead and compute Tukey's test as well, but I'm going to just go ahead and hit compute, and there you go. Okay, so we've got the sample means. So it spits out that familiar ANOVA table just like usual. We've got the sample means for each of these groups, and you'll notice that the sample means are not very different. So whether you have blue, brown, gray, or hazel eyes, your average height seems to be more or less right around 180 centimeters. So anyway, so not surprising that we will not be rejecting the null hypothesis here. Eye color and height have no correlation. So that's how you would run an analysis of variance. No need to run Tukey's test here because you're not rejecting the null hypothesis. But if you had to run Tukey's test, you could still do that. And it'll give you all Tukey's results as well. As far as graphs are concerned, for comparing a qualitative and quantitative variable, probably the best graphical summary, and I think we have practiced doing this a little bit, but probably the best graphical summary is to make a side-by-side box plot. Okay, and the way you do that is you go to Graph Box Plot. Under Select Columns, you choose the response variable, in this case height, and under Group By, you choose the explanatory variable, which in this case is eye color. And under grouping options, we want to plot groups for each column. Okay. Otherwise, it'll make a different table for each of your box plots. But we just want to see all of the box plots on the same graph. So that's what we'll do. All right. So let's practice. You go to Graph, Box Plot. We want to make box plots of the heights, and we want to group them by eye color. Oh, it's already on that setting. We want to plot groups for each column. Wait, is that what we want? Plot groups for each column? Yeah, plot groups for each column. So I guess that's its default setting, is to come that way. But we hit compute, and there you go. So you can see the box plot for the blue-eyed presidents, the box plot for the brown-eyed presidents, and so forth. And I mean, these things are pretty close together. There's pretty much no difference here between the groups. So again, not surprising that we fail to reject the null hypothesis in this case. Okay, so that's that. One last thing though to say about comparing a qualitative and quantitative variable. If the explanatory variable only has two different responses, in other words, if you only have two groups that you're going to be comparing, like let's say if we have the eye color example, but the only eye colors, let's say that all presidents only had blue or hazel eyes. There were no brown-eyed presidents, no gray-eyed presidents, right? In that case, you would only be comparing two means. Okay, you would be comparing the mean of the blue-eyed presidents and the mean of the hazel-eyed presidents, and so you don't run an ANOVA for that. You run a two-sample t-test. Now, this requires a little bit of extra work in StatCrunch because StatCrunch won't do this for us automatically. We have to manually group the data by handedness first. And the way you're going to do that is you go to Data, and then Arrange, and then Split. And once you do that, under the Select column, you'll choose the response variable, in this case height. And then under Split By, you'll choose the explanatory variable. So if we wanted to see if handedness had any bearing on height, then this is what we would do, and then we would run our two-sample t-test with data. Let me show you what I mean. So handedness, there are only two possible responses, right-handed and left-handed. And so we wouldn't run an ANOVA on that because we're only going to be comparing two means, and the ANOVA is for three or more means. So to group, so we want to see if handedness has any bearing on height. So we want to group the height by handedness and make two columns, right-handed heights and left-handed heights. So here's how you do that. You go to Data, Arrange, and Split. the column that we want to split is the heights column, and we want to split it by handedness. Split by handedness. So I'll hit compute, and then you'll notice that it makes these two columns, a left-handed height column and a right-handed height column. And now we can compare those two columns. We can run a two-sample t-test like we usually would. So stat, t-stats, two-sample with data. We want to compare the left-handed people to the right-handed people. And that's that. Oh, look, so there is this, so another statistically significant result here. So it looks like the sample difference is 4.19. So it looks like left-handed people are about 4 centimeters taller than right-handed. Well, left-handed presidents are 4 centimeters taller than right-handed presidents. So anyway, so that's kind of interesting. If you wanted, of course, you could compute those sample means. Go stat, summary stats columns, and we could compute the sample mean of those two things, and see that, yeah, left-handed presidents are slightly taller than right-handed presidents. Now again, we're dealing with small sample sizes here, so that could just be a coincidence. But anyway, that's how you would make that comparison. Okay, so that's how to compare a qualitative and quantitative variable. Last but not least, if you wanted to compare two quantitative variables, then you would do this by running a regression analysis. And as I said at the beginning of this video, we have talked about running regression analysis, but we didn't talk about hypothesis testing on regression analysis. StatCrunch will do this for us, though, so I want to talk about that. So if both variables are quantitative, we do this linear correlation. For example, if we wanted to know whether height has any bearing on the number of children, those are both quantitative variables, okay? And to see if these things are correlated, we would run a linear correlation test, okay? Now we're going to run this slightly different. Well, actually, no, that's not true. We're going to run it exactly the same way. We're going to go to stat, regression, and then simple linear. The x variable is the explanatory variable, and if we're wanting to see if height predicts the number of children you'll have, then height is going to be the explanatory variable. And the y variable is the response variable, in this case the number of children. But here's what's going to be different. It's going to spit out the correlation statistic, the regression equation, the scatter plot, all of the stuff that we looked at back in chapter 4, but it's also going to spit out hypothesis test results, which we just kind of ignored in the past. But now that we know about hypothesis testing, that information is actually really useful to us, because instead of having to compare the correlation statistic to the critical value from some table, we can just use the p-value to help us decide if there's a linear correlation. So here's how you do that. StatCrunch will do two hypothesis tests, one on the slope and one on the y-intercept. The one about the y-intercept isn't so important for us right now. It's the one about the slope that we care about. And the idea is that if the slope is 0, that means that the line would be flat, which would happen if you have a scatter diagram with dots kind of all over the page. So if there's no linear correlation, then we expect a slope of 0. If, on the other hand, the slope is not 0, then there is a linear correlation between the variables. And so the hypothesis test we run is the null hypothesis that the slope equals 0, no linear correlation. And then the alternative hypothesis could be left-tailed, right-tailed, or two-tailed. If you think there's a negative correlation, then you could set the hypothesis test to say slope is less than 0. If you think there's a positive correlation, you could set the alternative hypothesis to say slope greater than 0. But most likely you'll just run it two-tailed and just say slope not equal to 0. If the slope is not equal to 0, that means that there is a linear correlation between the variables. So in any case, the p-value of that hypothesis, if the p-value is less than alpha, then there's a linear correlation between the variables. So let me show you how this would work. We wanted to compare, what was it? Height to number of children. So if we wanted to see if height predicts the number of children that you're going to have, then we would run a correlation. So we would go to stat, where is it? Stat regression. Sorry. You go to stat regression and then simple linear. We want to see if height predicts number of children. We're going to perform this hypothesis test. I'm going to run it two-tailed because I don't really expect there to be any correlation, and if there is, then I don't know if the correlation would be negative or positive, so I'm just going to run it two-tailed and hit compute. Okay, so like I said, you get the correlation coefficient, which you can see is really close to 0. Probably there's not a correlation here. But here are the results of your hypothesis test, right? So for this, it's the results for the hypothesis test on the slope that we really want to look at. Okay, notice that the p-value here is 0.521. So we are not going to reject the null hypothesis, which means there's not a linear correlation between these variables. Surprise, surprise. So no linear correlation between the variables. Okay, that's all I have to say about that one. As far as graphs are concerned, the best graph when you're comparing two quantitative variables is probably just the scatter plot, which StatCrunch spits out with this hypothesis test. And yeah, you can see the dots are just all over the place. Man, this president was really prolific. Who was this? Let's see. This was John Tyler. Okay. John Tyler had 15 children, apparently. I don't know if this data is correct. I didn't really check it, so it could potentially be incorrect. But anyway, no linear correlation here. And again, this is a really good graph to include to kind of visualize that. Okay, that's it. So again, your goal in this project, you're not going to be analyzing the US president's data that we were just looking at. You're going to be analyzing the class survey data about cupcakes and you know, how tall you are and your favorite superhero and all of that stuff. But when you're doing that project, your goal is going to be to compare a few different sets of variables, right? And when you're comparing them, you're going to need to run some kind of hypothesis test. And so to figure out what kind of hypothesis test to run, you should ask yourself, are the two variables that I'm trying to compare, are they both qualitative? If so, you run a homogeneity proportions test. If one of them's qualitative and the other's quantitative, run an ANOVA. If they're both quantitative, run a linear correlation. And that's all the background information I think you need to successfully complete this project.